This is the 13th and final lecture for Chapter 2 for ODE, and in this lecture I'll discuss the center and spiral phase portraits, and just like the previous one, finding the eigenvalues is easy. That just falls out of the quadratic formula, but finding the corresponding and the correct eigenvectors is where the big difference is from the previous examples. Now the matrix that has complex eigenvalues, and that's what we're discussing here for the centers and the spirals, of course is a coefficient matrix. So we have A such that the trace, so the trace squared is less than 4D. Okay, and that is because, as you remember, the solution for the eigenvalues, well, first you had a characteristic polynomial. I'm writing this sort of for review. It's minus t lambda plus d. That equals 0. It's a quadratic function solvable by the quadratic formula if you can't factor it. And this is t squared minus 4d over 2. So if this is less than 0, the result will be complex. You have complex conjugates. So we have this particular matrix here. The trace is 2, and the determinant is, let's see, wait a minute, also 2. So t squared is less than 4d, and we're going to end up with complex eigenvalues. You can calculate those pretty easily. The eigenvalues are going to be 1 plus or minus I. Now the next step in solving this is to find the eigenvector, and we do it in the usual way. We're looking for v1 such that a minus lambda 1I is 0. Remember, this is complex. So when I put this through the equation, a wasn't complex, but this is complex, and I end up with a complex matrix here times v1, and that has to be 0. It should be a vector 0. Okay, so if you write this out in component form, you see, and perhaps you can deduce from this step right here, that eigenvector v1 is going to be complex. And in this case, here's the eigenvector v1. Okay. You can substitute that back into these equations to verify it. Now we could go ahead and try to find another vector v2, and then we have all kind of complex eigenvectors around, and we really want a real solution. So recall that for the harmonic oscillator, for the underdamped and the purely oscillatory case, we look for real solutions. We were using Euler's formula, and we're going to do something similar here. But we're going to stop right here with this eigenvector, and we'll just write it out, separating out the real and imaginary parts. Now I apologize. After I wrote all these notes, I try not to do this, but I have this A here and A here. So I duplicated the notation, and that's not a good idea. But I saw that too late. Okay, A up here is the coefficient matrix. This A here is a vector. In this case, the vector is 0, 1, because that's the real part of V1, and then B will be right here, multiplying I for the imaginary part of the vector. So we're going to use this eigenvector, and from this eigenvector and the complex eigenvalue, we're going to come up with two linearly independent real solutions. So we'll start by writing the solution associated with that complex eigenvalue and the first eigenvector. So this would be y1 here, e to the lambda 1t, again being complex, and it's the plus sign here because that's what we chose for the v1. You could do this just as easily using the negative sign and finding another vector. Okay, but here's the vector v1. Now by Euler's formula, e to the alpha plus I omega t can be written as e to the alpha t times sine omega t plus I cosine omega t. Okay, I just used Euler's formula to write it out, to write out the exponential form. The eigenvector we also wrote as a plus bi, writing the real and imaginary parts separately. Now we're going to multiply both of those together. So when we multiply them together, it's pretty easy. You end up with a real part here, and then you end up with this imaginary part here. And remember, a and b are real, they're just vectors. Now these two pieces are going to be linearly independent, and that will give us our solutions. So we aren't going to go looking for that second eigenvector. And here are the solutions. So this would be the first one, and this was a real part that we had on the previous slide, and here's the second one. So the general solution is a linear combination of these two because these two are linearly independent. You can verify that pretty easily yourself. You could even, I don't know, use a Wronskian on cosine and sine. You know, you can see that those are linearly independent. Okay, so here's why. C1 times all this plus C2 times all this. And now we had an example. It's kind of, I don't know, hard to follow without some sort of an example. So we had that initial example when I started this lecture, and we found that the eigenvalues were 1 plus and minus I. So that means this is alpha, and that means omega is 1. Okay, and then the A, and here's B, and that's because of V1. V1 was minus I, and 1 was the eigenvector. So separating that out into real and imaginary parts, here's that A. Again, A is a vector, not A is the matrix. B, and we're going to substitute all that into here and get our solution. You know, some people say you should keep rederiving things, and I don't think that's necessary. If you have derived things using only variables and all your steps, and you really understand it, then you can use the solution that you got that way as a template when you go to working with numerical examples. So here's that solution that we derived previously before we went to this example. Okay, remember this was that real part of multiplying the complex eigenvalue times the complex eigenvector and using Euler's formula. Okay, those are our two linearly independent solutions, and this is a linear combination of them. But we're going to substitute the values we had before. We had alpha was 1, omega was 1, so here's your alpha turning into 1, here's your omega turning into 1 throughout this, and then we had A and B, and you can see how those are just substituted. Okay, that's pretty easy. And now take advantage of these zeros. We've got e to the c1 e to the t, but this all becomes just one vector. Sine t for the first component here, that's just sine t because there's two negative signs here. There's a 0 here, so we have 1 times cosine t. So that's easier, and we get a similar easier vector when we make use of the zeros and the ones and multiply through. Okay, that's a solution. Well, the associated phase portraits are centers and spirals. If that alpha was 0 in the previous case, so that the eigenvalue is purely imaginary, then the phase portrait is a center. These are nested circles, nested ellipses, shapes like that. Okay, if the real part is not 0, but it's positive, positive here, then the phase portrait is a spiral source. It will be spiraling out from the origin. In this case, again, the only equilibrium solution is the origin. Okay, so it's spiraling out because it's a source from that equilibrium solution at the origin. If alpha is less than 0, then they're spiraling in for spiral sink. The spiral sink is your overdamped harmonic oscillator. This case right here is the example we just did, because alpha was 1, it was greater than 0. That would be a spiral source. So now for the rest of this lecture, I'd like to do 2 non-canonical examples. The first one will be a non-canonical center, and I'll use the coefficient matrix from the textbook on page 309, and here is that coefficient matrix. And the trace is 0. Okay, the determinant is 1. Obviously, t squared is less than 4d, so we expect that we will have complex eigenvalues. Here's the characteristic polynomial again. Well, sorry, the characteristic polynomial, as you know, we substitute for that, we get, remember, t is 0 here, so we just have lambda squared plus 1 equals 0, and the solution is plus or minus I. Okay? So we use a typical procedure to find that first eigenvector, and then we're going to break that into pieces. So here is that equation for the eigenvector is A minus lambda 1I, identity matrix, times V1 equals 0 as a vector. This is poor notation there. Okay. So if we work through those components, you know, just write out these as 2 equations and pick the easiest one to use. And from that you can get an eigenvector. Okay, so if I let this one, I'm sorry. Okay, here's the equation I'm going to work with, right here. All right, so I'll let this be 1. If this is 1, that dictates what Vx1 is, and here is the eigenvector. V1 is 3 minus I for the x component and 1 for the y component. And then break it into the 2 pieces, real and imaginary. That's the A and the B. And pull out the I, of course, from the B. Okay, now we have everything we need. We can go back and use that solution we had a few minutes ago. So here was the solution that we derived in general. E to the alpha t, here's that, then A cosine omega t minus B sine omega t, and here's for the second part of it. Okay, alpha is going to be 0. This was purely imaginary. Omega was 1, so we have kind of an easy example here. And here was the A vector and B. Those are the 2 vectors that combined make up the complex eigenvector V1. And all we have to do is substitute that into this equation, and then again taking advantage of some of the zeros and doing some multiplication in here, we have the 2 solutions for x and y. C1 times 3 cosine t plus sine t plus C2 times 3 sine t minus cosine t. That's the x component. The y component is similar. C1 cosine t plus C2 sine t. And now I'll just go through again the exercise of writing those constants C1 in terms of the initial conditions. This might be something you wish you or hoped you'd never see again, but here it is. Okay, so what's the initial condition? We need initial conditions on the vector y of t. And remember, it had components x of t, y of t. It was a solution vector. So time t equals 0, we can say that x at 0 is x naught, y at 0 is y naught. And we would like to have C1 and C2 written in terms of them, so that every time we have a new initial condition, all we have to do is substitute. We don't have to go back and evaluate C1 and C2 over and over again. So if we take our solution that we had on the previous page and evaluate that at t equals 0, we have x, remember all those sign terms go away, which is nice, x naught y naught, which is the solution at 0, and here is from the solution that we derived with the C1s and C2s in it. You can write some equations, and then from that you can just solve this algebraically and find values for C1 and C2. Obviously C1 is y naught, that's easy, and C2 isn't far behind. And now we have the total completed example. These are the solutions for that um, for that coefficient matrix, pertaining to that coefficient matrix that ended up with complex eigenvectors, eigenvalues, and of course a complex eigenvalue. These are the two solutions, x and the y. And here, instead of C1 and C2, we've used our solutions. And now, if you want to evaluate solution curves, all you have to do is give different values of x naught and y naught, and then the t dependence is in these vectors. And here's a phase portrait corresponding to that case. You'd have a hard time drawing this by hand. You have to use some kind of computer program to do it. There's some software that came with the textbook, but I have not, I don't know, it's got some glitches in it. Not glitches, it takes a little bit of time to learn how to use that software. I just use dplot. That's a plotting program that I like. I just plotted up the solution. Here are the solution curves, or examples of the solution curves. Notice they're oscillatory. There is no attenuation because there was no damping. Remember, this is a purely oscillatory case where attenuation was 0. If it was going to be a circle, if the phase portrait was a circle, these magnitudes would be the same, but they're not. They're very different, and that's what gives us that elliptical pattern instead of the circles for the canonical center. Now I'll do an example for a spiral source. Here's another coefficient matrix. This is the one I'm going to use for this spiral source. The trace is 0.3, the determinant is 0.1. So t squared is less than 4d, so I expect complex eigenvectors. Here's the characteristic equation. I'm going to use a quadratic formula to solve for it, and I end up with these complex eigenvalues. So now we have to do some work to find that eigenvector. I keep repeating these patterns over and over for you so that hopefully they're just going into your mind and you won't have to spend time trying to study them. To find the eigenvector, we know the eigenvalues, so we have A minus lambda, in case we're using the first eigenvector, times I will give us the first eigenvalue will give us the first eigenvector. Here are the components for that eigenvector. Here is A minus lambda I. It's very complex. I'm going to write them out. Again, we'll try to do something simple. So I'll set Vx1 equal to 1 and then solve for Vy1, and this is what I get for my eigenvector. It's complex. I separate out the real part, call that vector A, and the imaginary part, I call that vector B. At this point, I have everything I need for the solution. What's alpha? Okay, 0.15. Omega was 0.28. And here's A, and here's B. So now I can go use the solution that I derived previously. And here's that solution written again for reference. It's right here. Now I'll substitute the alpha, the omega, and the vector A and vector B, and I end up with the solution. There's only one zero. Well, actually, one here and one here. This is a non-canonical example, so we don't expect those really simple forms for solutions, but it's all tractable. Actually, all this stuff is pretty much plug and chug once you understand it. Okay. Here are the solutions. That 0 helped us with the x, but the y still has quite a few terms in it. Okay? And you can tell this is a spiral source because here's alpha, and this alpha is greater than 0. So it's going to be spiraling away from the equilibrium solution at the origin. I went through the exercise here of rewriting the constants in terms of the initial conditions. So here's C1 and C2. The initial conditions are x naught and y naught, which is the value of the solutions where they start, wherever that those will vary, of course. Equating these two terms, here's y at 0. This is from the solution we just derived. Of course, all the sign terms nicely go away when t is 0. And we end up with the constants. C1 is x naught, C2 is y naught minus the alpha times x naught over omega. If you recall from the harmonic oscillator, we had similar results. Well, actually identical results. And here's our spiral source. There's the equilibrium solution right there, and this is a spiral source. It's a source because the alpha was greater than 0. You see where these, in the direction field, these are pointing out away, going towards infinity, so a solution would start here. In backwards time, it's approaching the equilibrium, but in forward time, it's going out here and maybe making one turn heading off towards infinity. And here's some sample solution curves. Okay, making that one bend around here, you can see that this is sort of the bend that these make, and then it's heading off towards infinity, both of them going towards minus infinity as they move off in this case. Okay, so that's the last lecture for chapter 2. Again, we divided chapter 2 into 2 parts. The first part, lectures 1 through 6, were dedicated to second order differential equations, and lectures 7 through to 13 are for the planar systems. And in this case, we found, in both cases, we found there would be a characteristic polynomial that's just a quadratic function. We can solve it using quadratic formula or factoring, whatever's handy. For the planar systems, we had to go on and find these eigenvectors, and for every group of cases of phase portraits, the finding of the eigenvectors was different. We have the saddle source and sink pattern with 2 distinct real eigenvalues, and from that we were able to get 2 linearly independent eigenvectors. Then we have the case where we have 2 equal eigenvalues, and we had 2 cases there. In one case, we can get 2 linearly independent eigenvectors. We end up with the ray pattern. When we can't get 2 linearly independent eigenvectors, we only have one of them, then we have a way to bring in another solution, and from that we can calculate the single tangent pattern. The 0 eigenvalue, which really shouldn't stand out like it does, or it shouldn't seem to, becomes a very special case in which the phase portraits are lines, and the equilibrium solution is a line of equilibrium points to the origin. All the other cases have only the trivial equilibrium solution at the origin. And then the final case is that of complex eigenvalues, and in this case we have centers or spirals. The next chapter will be on nonlinear equations.